Dear students, welcome to session 19 of this GPU architecture lecture. We're today going to finish off this part 3 of the lecture that is called the graphics pipeline, and that is concerned with architecture of GPUs. And we're already almost through. We talked about the graphics pipeline last time, and we talked about the graphics pipeline along the various stages. And today we're going to finish off this part by discussing a couple of miscellaneous topics that are related to the graphics pipeline. And the very first topic that I'm going to discuss is synchronization. And synchronization just arises due to the scalability requirements that we discussed earlier in the lecture. And one of the scalability requirements was a scalable input data rate. That is, when the user submits input data like vertices or textures to the command stream, then it is important that the pipeline is installed by that. And on traditional graphics cards and graphics processors, that was way simpler because we usually only ever had a single graphics context and a single thread that would submit draw commands or that would submit data to the GPU, so the host interface was strictly serial. And on modern graphics processors, this is quite different. Like on modern graphics processors, we usually have multiple command buffers, and we also potentially have multiple command processors that process those command buffers on the GPU. And we also commonly have multiple applications that concurrently submit commands. So we have command buffers from different applications, but we also have single applications that have multiple graphics contexts and therefore also have multiple command buffers that they submit to. Typical examples would be when we have a multi-GPU setup where we have multiple threads using multiple GPUs, and then in the end their results are composited. So the setup here is much more heterogeneous when it comes to command buffers, and we usually also don't have those ordinary command buffers where we submit draw commands to or synchronization commands. But we also usually have dedicated DMA buffers that are there for texture data or for vertex data, in order to not stall all the other commands that are concerned, for instance, with different draw calls. And because of the heterogeneity of this setup, we just need synchronization. So the first synchronization means that I'm going to discuss instead of barrier and fence synchronization. And the barriers or fences, dependent upon which API you use, they're either called one or the other, so barrier or fence. They're basically just synchronization commands that are entered into the regular command stream. And a barrier usually means that we have to wait on this synchronization primitive. So a barrier is a synchronization primitive where we have multiple execution units that have to wait on this barrier. Why I'm saying execution unit here and not thread, there's a very subtle difference, because usually when we're talking about barriers and fences and synchronization on the GPU in general, it's important to note that those primitives don't block the CPU. This type of synchronization happens on the GPU, and we submit those synchronization primitives using dedicated tokens that are basically just put into the command stream. And this is very similar to the tokens that we discussed earlier when we talked about how interrupt handling is performed on the GPU. You remember that we had our GPU with the Microsoft Windows display driver model, that we had the GPU rendering, and then finally when the GPU finished rendering, we had the GPU inform the host that rendering was finished, and we saw that this was done using a token. The host would enter a token into the command stream, and the GPU would encounter that token, and as soon as it encountered that token, it would set an interrupt in order for the host to know that rendering finished. And the handling of synchronization primitives is actually quite similar, where we usually have tokens that are entered into the command stream, and the GPU knows that those are used for synchronization. And let's just walk through a quick example. So for the sake of our discussion, let us consider this very simple rendering example with two GPUs. We have GPU 0 here on the left-hand side in blue, and we have GPU 1 that I'm depicting in red. And then we have this geometry that consists of both opaque surfaces as well as of semi-transparent surfaces. And they both need to be rendered, and we have this typical sort last assignment. That is, we have an assignment of geometry, which is unique, And that means that the assignment of fragments that will later result from rendering to raster positions isn't unique. So in general, like GPU 0 can produce fragments and GPU 1 can produce fragments, and it is unclear which raster positions those fragments will belong to. Like there's no unique assignment, and in general, like fragments that are generated by GPU 0 might overlap fragments that are generated on GPU 1. Like now we are rendering the scene like from this viewpoint, and a very common approach to do so is to have multiple passes for both opaque and for semi-transparent geometry. Like in general, we would render the opaque geometry first into the depth buffer, and like what I'm illustrating here is a camera coordinate system where we're rendering into the depth buffer and into the color buffer. And we would start with the opaque geometry, and then at the same time, like concurrently with what GPU 0 does, we would also render the geometry on GPU 1. So this could happen concurrently. And like both GPUs would now fill the depth buffer, that is, they would generate fragments, and that fragments would be written into the depth buffer. And the depth test would decide which fragment is overwritten and which fragment is visible in the frame buffer. Like only dependent upon the value of z, so only dependent on the depth. Because the geometry is opaque, we can just use the depth buffer to decide which fragments are in the front and which are in the back. So all this can happen concurrently. Like of course there's some GPU synchronization when fragments are written to the depth buffer, but we're of course not concerned with that because the GPU does that first. With the semi-transparent geometry, it's of course different, because semi-transparent geometry needs to be composited. That is, when we draw semi-transparent geometry, then surfaces behind that semi-transparent geometry are generally visible. And more than that, we even have to sort it into visibility order. And therefore, we would usually have a second pass where we only render the transparent geometry, and the transparent geometry would be rendered over the depth buffer that was already filled via the opaque geometry by the first pass. And this is the general setting we're in. That is, apparently there's a synchronization need in that the two contexts that are bound to the two GPUs need to synchronize. And in particular, it's of course important to note that order matters here. So the order in which the semi-transparent geometry is drawn over the depth buffer is important, because we learned earlier that over-compositing, back-to-front compositing or front-to-back compositing is order dependent. That is, we need to sort the geometry into visibility order before we render it, and therefore it is important in which order the two GPUs render their semi-transparent geometry over the already filled depth buffer. And in order to achieve this, we have to make sure that the order in which the GPUs render is synchronized. So, and even legacy APIs nowadays support simple synchronization primitives on the GPU, like fences and barriers, and also semaphores to ensure the correct order of the draw commands. And like what I'm showing here is what it would typically look like if you would use an API like OpenGL for synchronization of two contexts, like the one that we just discussed. Like we have context 1 that is associated with GPU number 1, and we have context 2 that is associated with GPU number 2. And we're in this setting where we first draw the opaque geometry, and then we draw the transparent geometry, but we have to draw this transparent geometry in order. And therefore we start, like we would have one of the GPUs first clear the color buffer, like write the color black into the color buffer. And then we would have a synchronization, and the synchronization would happen using a fence, like a fence or a barrier, where all the threads that are concerned with rendering wait for and until the color buffer is cleared. And then we would have both contexts at the same time draw their opaque geometry into the color and depth buffer. And then there would be another synchronization point, like a barrier. And then we would have context 1 draw its half of the transparent geometry, like its share of the transparent geometry. Like, because we have to do this in order, like the visibility order would prescribe that we have to render in context 1 first. And then we would, very similar to what we discussed in one of the exercises, use a semaphore to ensure the order between the two. Like we can use semaphore primitives on the GPU, and in that regard, they are very similar to semaphores on the CPU in that they help us to ensure a certain order of execution. So we will use a semaphore primitive for that. And then in the end, we would have another fence where both contexts wait on and where all threads and thread groups from the two contexts wait on. And then in the end, we will present the color buffer. And this would be a very basic way of synchronization. And this type of synchronization is even available in legacy APIs like OpenGL. And once again, this very important remark, like when I'm calling sync threads here or semaphore notify, and there are, like OpenGL has equivalent calls for that, they're quite similar. When I call them, this won't block CPU execution. Like those shouldn't be confused with CPU synchronization primitives. Rather than that, they are GPU commands. And as GPU commands, they go into the GPU command stream. They usually manifest there as tokens. And the GPU will encounter them and will then know that we have to synchronize with certain other commands, maybe from another context or from another thread group. But they will not block the CPU execution. Because this is the whole concept of the asynchronous host interface that we discussed. We have the CPU and the GPU operate concurrently, and we have basically the CPU telling the GPU in which order the draw commands need to be specified, if any. Like, if the order doesn't matter, the GPU is pretty much free to do what it wants. And in order to synchronize between the two, the CPU enters synchronization tokens into the command stream, and the GPU can figure out from that the order in which the commands are executed. So, and those are the typical synchronization primitives that are available on GPUs and that are provided by the APIs, like both OpenGL as well as modern APIs like Vulkan or Direct3D12. Will provide us with barriers and fences, and also other synchronization primitives, but those are quite common. And synchronization can happen with different granularity. Like we can synchronize on a per draw call level, where we synchronize in regard to a whole draw call, like we saw in the example before. But the granularity that we can synchronize on isn't restricted to that. Like we can even synchronize threads within a single thread group, like within a single work. And in general, the best practice here is to avoid synchronizing the whole device, like stalling the whole pipeline, and really only synchronizing on the granularity that is required. Like we'll usually try to only synchronize those execution paths that require synchronization and avoid complete pipeline stalls. So in the example that I showed before with the two contexts, this was very typical for how synchronization works with legacy APIs such as OpenGL or older DirectX, in that we would only synchronize when there are more than one context. Like when we have two contexts or multiple contexts, then we have to synchronize between them, and then we have to specify what the interdependencies are. But in general, if there's only one context that the application uses to render, and this is actually quite typical, like usually an application would only have one context unless we have like multiple GPUs, or unless we have some special requirements for the application, we would have just one context that is used for rendering. Then we wouldn't have to take care of synchronization at all. And with modern APIs such as Vulkan or DirectX 12, this is quite different actually, because we usually have to synchronize in general. Like we have to synchronize even if there is only one thread that performs rendering. Like Vulkan doesn't think in contexts, so it's quite different in this regard than OpenGL is. So we don't have this notion of two contexts being synchronized, but rather than that, we have multiple draw calls that have to be synchronized. And if we don't do that, like if we don't specify the interdependencies between those draw calls, then the GPU will do whatever it wants. Like it will just retire the commands in whatever order they occur in, and without waiting for certain commands to be finished before other commands are allowed to start. And the APIs that those modern APIs provide are so-called event-based APIs. So the idea is that we again like place tokens in the command stream, and those tokens are just associated with events. And like a typical event could be that a draw call finished. And then we are allowed to specify interdependencies between those events, Like a rather typical synchronization would look like this, where we have like draw call n and draw call n+1 and draw call n+2, and those are just synchronized on their finished events. Like the second draw call may only start after the first draw call completely finished execution. And the same is true for the second draw call. And we would specify events with those APIs, and those events would just be associated with the time when rendering finished, and then we would synchronize the pipeline on that. But in fact, the granularity with those APIs that we have available is much finer. Like we could, for instance, have certain draw calls that are allowed to be executed at the same time because there's no interdependency between them. And then we would like have a synchronization of just those events that are dependent on each other. Like in this example here, we have the first draw call, and the second and the third draw call, they are allowed to overlap. And then we just specify an event that the second and third draw call wait on in order to synchronize with the very first draw call. And then there's also this concept that is called a split barrier that is, for instance, provided as an API primitive by DirectX and Direct3D12. And the idea here is that we synchronize every even and every odd draw call. Like we have draw call 1 and draw call 3 here, and those are synchronized on their finished events. And then we have the even draw calls, and here we would like, if there was a draw call 4, that draw call 4 would only be allowed to start execution after draw call 2 finished. So we have this type of granularity, and we even have finer granularity, and that we can synchronize on certain pipeline stages. Like Vulkan or DirectX 12, they allow us to synchronize, for instance, when a certain draw call finished vertex shader execution. Like in certain cases, it might be allowable that a draw call starts when the first draw call, like the previous draw call, finished execution of a certain pipeline stage. Because at that point, it generates some output, and we're dependent upon that output. And after that output is available, we start the second draw call. And like when I'm talking of draw calls here, like in general, I'm referring to every type of call on the GPU here. So this can also include like compute calls. We will later also talk about compute on GPUs, and we will talk more about synchronization when it comes to this. Like the granularity here is like we are, on the one hand, we have granularity where we have synchronization on a per call level. But we can actually also synchronize on a per core level, like on a level where we synchronize individual threads in warps or in thread groups. So we will revisit this concept of synchronization. And for the time being, what is important to keep in mind is that synchronization, on the one hand, doesn't block CPU execution, so it makes use of the asynchronous host interface of the GPU. And those synchronization primitives that we use, they usually manifest as some type of token in the command stream. And while with legacy APIs, we're mostly only allowed to synchronize between different contexts, and those different contexts usually involve different threads that make use of one or of more GPUs. The granularity with newer APIs such as Vulkan or Direct3D12 is much finer, where we can synchronize on the level of different draw calls and even on the level of different pipeline stages of those draw calls. And that allows us to overlap execution on the GPU with a very fine granularity and provides us with very much control over how the parallelism on the GPU is being made use of. But it also places a certain burden on the shoulders of the developer, who now is responsible for always taking care of synchronization, even if the execution pattern that is used is mostly serial. So, and another of those miscellaneous topics that I briefly want to touch upon is GPU cache hierarchies. Like, when we talked about CPUs, we already touched upon cache hierarchies in general, and in particular when we talked about NUMA systems and when we talked about shared memory systems. And as a matter of fact, GPU cache hierarchy is actually quite different, but on the other hand, there's also this problem that the documentation is actually quite scarce. So therefore, we will only very briefly touch upon this topic, and in particular because the exact layout of the caches is not known for most of the architectures, and there's a bit of documentation out there, like for instance AMD is somewhat better at documenting their architectures. And this is an exemplary illustration that I took from the GCN architecture white paper. And
what you can see here is that you have a very heterogeneous architecture. Like you have this relatively large L2 cache, and then you have what I earlier called an SM when we talked about NVIDIA, like what was a shading a multiprocessor there, and AMD happens to call this a compute unit, but nevertheless they're like basically the same thing. And then you can say that we have, with this architecture, that we have both shared as well as local L1 caches. And then we have, on the other hand, we have this that L2 cache that this processor unit is connected to. Now, on the other hand, we have those fixed function units. Like we have the command processor, and the command processor directly talks to the L2 cache. And then we have shader controllers, texture units that have their own L1 cache and that go through L2 and are thereby connected to the video memory. And then we have a frame buffer which has an L1 cache but isn't connected to L2. And then in the end, there are even those DMA engines that are concerned with transferring texels and vertices, and they aren't even cached, but directly write to DDR memory. So we have this very heterogeneous architecture, and in particular, we don't have like a symmetrical cache hierarchy as we saw them with NUMA CPUs. So they're actually quite different in this regard, and we have like several units which have their own local L1s, and some of them have like a local and a shared L1. Some of them are connected to L2, some of them aren't, and the DMA engines don't even go through the cache hierarchy at all. And like this is a simplified illustration. Like when you read through the white paper, you will see that there's not a single large L2, but a couple, and that there's obviously like a couple of texture units and a couple of ROPs that are concerned with frame buffer operations. And the architecture is actually quite different than a typical NUMA system. And with the NUMA systems, we learned that there are cache coherency protocols, and those cache coherency protocols would ensure that local caches would be kept coherent, and we had those complex state machines that would tag the various cache blocks with a state, and the state would tell us if the cache block was currently in a modified state, or if it was in a state that it was never even touched upon, or if it was shared. And with GPUs, we just don't have that. Like with GPUs, we basically have models where every compute unit has its own L1, and we have a cache hierarchy that is similar to what I'm showing here. And whenever there's a write access, then data will just be flushed to memory. Like from a perspective of what we discussed in the context of NUMA, this is of course pretty inefficient because we have lots of memory writes that occur in general. But from a perspective of a GPU, this is actually the only way to efficiently implement a complex cache hierarchy on top of all those compute units, because usually you will have like a couple hundred of those CUs, of those compute units, or of those shader cores. Then on the other hand, you have this very heterogeneous architecture where there's a couple of fixed function units that also go through the same cache hierarchy in one or the other way. And for those architectures, it's usually just not viable to implement protocols like the MESI protocol that we discussed earlier. And I mean, if you think about it, this actually makes sense. Like with NUMA architectures, we have those cache hierarchies that are optimized for, on the one hand, for local reads, so that they are still efficient. And on the other hand, we had a deferred model that was optimized for write accesses. Like when there was a write access, then we would try to defer costly operations like those that go through memory or that go through buses. We would try to defer them as much as possible so that we can operate on the cache and on the data that is currently in the cache as long as possible. And when we think of how a GPU operates, like in particular the GPU and the execution model that is associated with the GPU to a large degree is fixed. So the memory access patterns are actually known. And what, for instance, is typical is that write accesses go to certain memory positions that are associated with raster positions. Like it is, on the one hand, known a priori what the memory access patterns will be. And on the other hand, it is also known to some degree, like for instance, to which memory locations a raster engine might write, or to which memory position a fragment shader might write. And if you also think about those memory access patterns, then you will find that certain writes are pretty exclusive. Like, for instance, if you have the vertex shader and the vertex shader operates only on its own share of vertices, then the write operations will also only go to the output attributes that are associated with those very vertices. And that means that we have more or less exclusive writes, and the optimization patterns are actually quite different than the optimizations that one would employ to write accesses that are pretty random. Like when we're on a CPU and the application pretty much determines where write accesses goes, it's quite different than an architecture where write accesses usually go to locations where we have an idea where the processor will write to. And therefore, the GPUs in general don't have to employ such complicated cache coherency protocols as we usually find them on CPUs with NUMA execution modes. And there are also some other notable differences between caches on the CPU and caches on the GPU. And on the GPU, as you can also see from this illustration, caches are usually quite scattered. So we have caches that are associated with those fixed function units and also with the compute units. And we usually have many caches, as we usually also have many cores. And as a consequence of that, the individual caches usually are quite small in comparison to the caches on CPUs. And also, in contrast to caches on CPUs, the memory access latencies are usually a bit higher. Like, quite often, the memory access latency is actually an order of magnitude slower than the memory accesses to caches on a CPU. We will later also learn about so-called shared memory when we talk about CUDA programming, and shared memory is basically yet another type of L1 that is associated with the shader cores, like with what is called a CU here. And this is basically like a programmable L1 cache. So the architectures are quite heterogeneous and quite different from the typical cache hierarchies that we know from CPU architectures. And this is just to give you an example to illustrate how complex and heterogeneous a typical cache hierarchy of a GPU is. And the documentation actually is quite scarce, so it's hard to tell for the other architectures. Like, this is an illustration that is from a document from NVIDIA, and this also illustrates something that is quite typical for GPUs. And this is the data flow through the cache hierarchy. So no matter which functional units are actually connected to the cache, like no matter what the exact hierarchy looks like, what is a very common theme is that certain operations go through memory and certain operations don't go through memory but just only go through caches. Like in a typical GPU pipeline, we have vertex fetch, that fetches vertex and vertex-related data, so attributes, fetches them from main memory. And then when we perform the various stages of the pipeline, all those operations go through L1 or L2. This is again the buffer paradigm that we discussed earlier, where we have this bulk data that is fetched into the pipeline, and then we process that data in a streaming fashion. And whenever we process like a bunch of vertices, like a fraction of the data, we do so by using small buffers, and those small buffers are located in L1 or in L2 memory. And this is true for the whole pipeline. Like, those memory accesses along the whole pipeline usually go through L1 and then through L2. And then only in the end, like when we have our fragment and raster output operations, we again go through DDR memory because we finally have to write data to the frame buffer. Like, whichever transformations are applied to the vertices that are initially fetched, then go through the vertex transform cache and are subject to clipping operations and primitive assembly. The pipeline ensures that all the operations have the data staying on the chip, and that there is no communication with actual DDR memory. And only after fragment processing, when we have to resolve visibility, like when the depth test is actually evaluated, then we have to write to DDR memory, and then the raster output operations will read from the depth buffer and will read from the color buffer, and will finally write output that can be accessed by the display controller. And this is pretty essential to how GPUs operate. so that they load a bunch of data items, like a bunch of vertices, and keep them in on-chip memory as long as possible, and process them and write temporary results to on-chip memory, and only in the very end, where we resolve visibility and where we write the final output to the display, we actually have to perform real writes to DDR memory. And this is a quite typical scheme for GPUs. This is an illustration by NVIDIA, but it is conceivable that the GPUs by all the other vendors operate in a very similar fashion.
So one final topic that I want to touch upon, but only very briefly, is that of how mobile GPUs operate. And for that, we should remind ourselves that GPUs really are tiny distributed memory systems, in a sense that GPUs at the very beginning load all the data into caches, and those caches are highly distributed. That is, we have like hundreds to thousands of cores, and those cores have like shared caches, but we still have like hundreds of those caches. And the GPU loads a part of the workload into the caches, like as it's available in on-chip memory, and then operates on that. And that basically makes the GPU a tiny distributed memory system, in that every core has its own local memory that can be accessed with a latency that is similar to that of accessing a cache. And when taking that view, like when considering a GPU as a distributed memory system, then we can also reason about the algorithm that is implemented on the GPU in the same way that we reasoned about distributed memory systems when we discussed Molnar's taxonomy, when we discussed how distributed workloads are handled on the GPU. So traditionally, GPUs have been sort-last systems, in a sense that the GPUs would operate independently until the very end, where the GPU has to assure API order. So, and up until that, the GPUs would operate in a way where the whole workload could be processed more or less independently. And then at certain times, when executing the rasterization pipeline, we have those synchronization points, like right after the scan conversion stage or right after the fragment processing stage. And in the very end, the GPU would ensure API order. So, and because the GPU doesn't process the whole workload at once, but the data is rather streamed through the GPU and through the on-chip memory of the GPU, people would call that immediate mode rendering. Like, this shouldn't be confused with immediate mode APIs that we also discussed. Like, it's only remotely related. But it actually rather means that the GPU will only process a certain portion of the overall workload at once, then retire that workload, draw that workload into the buffer that is currently bound for rendering, like usually into the back buffer, and then process parts of the workload immediately, and then would retire that, and then would free the areas of the chip again that would hold the next portion of the workload, then process that, and then composite that on top of what is already in the back buffer. And because of that behavior, people would call that immediate mode rendering. And GPUs on mobile architectures actually operate quite similarly, only that they employ so-called tile-based rendering. Tile-based rendering is just the exact same tiles that we discussed when we talked about sort-middle architectures, where we have basically this mix of a screen space distribution and of a object space distribution of the workload that is rendered. Like, we're not talking the tiles of the raster engines here, but as a matter of fact, what we're actually talking about is like a priori and in the very beginning distributing the whole screen into tiles and then basically executing the rasterization pipeline per these tiles, like the whole pipeline, not only a step. Like, the raster engines would basically only be a single stage that would operate in a tiled fashion. But with this type of paradigm, we would basically subdivide the screen into tiles, into relatively large tiles, as a matter of fact, like usually into something like 128 by 128, maybe even bigger. And then we would basically execute the rasterization pipeline for each of those tiles independently. And here's the basic idea. Like with a immediate mode rendering architecture, you would have the GPU and the graphics pipeline being bound to the whole screen space region that we're rendering for, like the whole viewport or the window that we're rendering into. And then when the user submits a rendering workload like triangles, those triangles are immediately composited into the back buffer or into the front buffer or whatever buffer is currently bound for rendering. And with a tile-based architecture, like with a sort middle architecture, we would have a separate graphics pipeline per screen space tile. And that separate graphics pipeline would also start execution independently of all the others. Like it would start execution and work on its share of the workload. Like the triangles would be processed to the cores that are responsible to operate on this tile. And then at the same time, the architecture would also submit the same triangles to all the other tiles, and which would start working on those workloads independently and would retire them independently. And then in the end, like we would have our tiles being rendered independently, and then there would be some synchronization where the final image is ready and we could swap buffers in order to display the image. So in the deal with this execution mode is that we now require an extra stage in the overall graphics pipeline. Like the extra stage that we now require is binning. So here I'm showing a screen space subdivision into 4 tiles. And in order to bin the workload appropriately, we just take the user input, like the user inputs a bunch of triangles, and then we basically do what we also discussed when we talked about sort middle rendering, where we had this screen space subdivision, and then we very coarsely mapped the geometry to screen space tiles, and we do the very same thing here. Like we project those to the tiles and bin them to the processors that are responsible for the various tiles. Like we take the first triangle and we determine which tiles are overlapped, and then we assign that triangle to the bins that are associated with the processors that work on those tiles. We do this with the remaining triangles, like with the overall workload, until all the triangles are binned into their processors, and then finally we can start operating on them. But we can only do that after all triangles have been assigned to bins. Like this is basically due to API order, so that we can make sure that the triangles are still processed in the correct order. And therefore, we have on the one hand, we have this binning process, and before we can start rendering, there is synchronization. That is, the tile processors have to wait at a barrier until all the user input was received, and only then can we start rendering. So we have an extra stage in the pipeline for binning, and we also have synchronization. And only then can we start rendering. So that is the overall execution mode on mobile graphics processors, where screen space is subdivided into relatively large tiles, and then we have this a priori binning step before the graphics pipeline can start to execute. And therefore we have this extra latency because we have to synchronize before any actual work can happen. And the idea behind this is to increase locality. Like when we have this assignment of workload and of triangles to tiles, we have much better spatial locality than we would have with a immediate mode renderer that would be responsible for the whole screen space. And as we have spatial locality, we make much better use of caches, and we also make much better use of the available bandwidth. And if you recall our discussion on dynamic memory in one of the earlier sessions, then you remember that accesses to dynamic memory and dynamic memory in general is quite cost intensive, and it also consumes quite a lot of energy. And generally, when there's fewer movements to and from dynamic memory, so to and from DDR memory, then we can also save on energy consumption. And this is actually the whole deal with mobile architectures. So the idea with mobile architectures is to increase spatial locality. Due to spatial locality, the actual data, like the triangle workload, is closer to the processors that actually work on that very workload. And this is achieved by those tiled approaches that guarantee beneficial spatial locality. But on the other hand, we buy that at relatively high latency, as we have this extra synchronization step in the pipeline, and the pipeline can really only start processing after the user input has been processed and the triangles have been projected to the screen space tiles. So mobile GPUs would traditionally use tiled architectures where there is this extra binning and synchronization step which introduces additional latency, but on the other hand we have increased spatial locality. And traditionally, desktop GPUs also used immediate mode rendering without tiles. And quite interestingly, a couple of years ago, NVIDIA started to switch over to tiled rendering in their desktop GPU architectures. Like with the Maxwell architecture, NVIDIA is known to use tiled rendering. Like this is nothing that NVIDIA published, but there are certain experiments that you can do with shader applications that allow us to assess the order in which triangles are retired. And with those experiments, it was possible to find out that with the Maxwell architecture, NVIDIA started to use tiled rendering even on desktop architectures. And this is quite noteworthy. It's hard to tell what the motivation was for NVIDIA to switch over to a tiled architecture. Like, spatial locality in general is a good idea, and it's also a good idea to reduce overall energy consumption on a graphics processor for several reasons, and not just for reasons that a potential battery in a mobile device might be drained faster than necessary. So the reasons for NVIDIA to switch over to such an architecture, they of course remain unknown to us, but it's still quite noteworthy that this architecture has been adopted by the vendors and is nowadays even used on desktop GPUs. So, and with that, we're already at the end of this relatively theoretical part of the lecture that is concerned with GPU architectures. And we learned quite a lot. And first and foremost, we learned that GPU architectures are driven by scalability concerns. So GPUs, they are still coprocessors, and being coprocessors, they're never allowed to block the overall system execution. And we learned about the various data rates, so about the input data rate, or about the texture rate, about the pixel rate, and none of those rates is allowed, none of the stages where those rates are important is allowed to starve the overall pipeline execution. And that, to a large degree, influences the overall design of GPU architectures as we know them nowadays, where we have this very pipelined architecture where the data is basically streamed through, and the data is always pretty close by to the processors that actually operate on them, where we have most of the data being in on-chip memory most of the time. And nevertheless, GPU architectures are quite heterogeneous in that they evolved quite a bit over time. Like, we have those fixed function units, like the raster engines, like the ROPs, or like texture units. And then on the other hand, we also have programmable hardware that in particular is highly parallel. And the architectures are designed in the way that regardless of those heterogeneity, neither of the stages will actually starve any of the other stages, nor the host for that matter. And those concerns, like the scalability concerns that we discussed in the very beginning, they influence to a large degree how GPU architectures have evolved over time. And it's also important to note that GPUs exhibit parallelism along the whole pipeline. As they are being coprocessors, we have this asynchronous host interface where the data is submitted asynchronously to the GPU and then is processed asynchronously to the GPU, and in the meantime the CPU can perform other tasks.
And the asynchronous host interface in general is also influenced by the fact that operating systems are multi-user and multi-process operating systems. That means we have multiple processes that can submit work to the GPU. And we, on the other hand, also have all these stages of the graphics pipeline that are in and of themselves relatively parallel. Like we have the highly parallel vertex and fragment stages. And then in between, we have the rasterization stage, which is also parallel, but which has a different kind of parallelism, and that we usually have fewer raster engines, in that the stage is not programmable, in that it uses fixed function hardware, and in that it generally operates differently than how a shader core would execute. So, and then there's of course this general characteristic that whenever we move data on the GPU, like be it from one on-chip memory region to another on-chip memory region, or be it from GPU DDR memory to the chip, be it from the host over PCI Express to the GPU, that usually bandwidth is relatively high, and at the same time we have relatively high latency. So the overall execution model here is one where we should usually transfer a lot of data at once, and then we should make sure that there is enough computation so that we can hide the latency from this large data transfer. And GPU architectures, in fact, lend themselves pretty well to that, because there is all this parallelism and the various threads that operate at the same time. And given that there is enough computational workload, so like arithmetic instructions that are executed, then the GPU can very effectively hide that latency by at the same time performing computations. And this is one of the most important characteristics of the GPU, that there is on the one hand very high latency, on the other hand there's a very high bandwidth, and then it's important that we can hide that latency by performing computations at the same time. And for those reasons, like as a consequence of that, because the latency is relatively high, things like texture compression and cache hierarchies play a relatively important role on GPUs. So in the end, there's a bit of literature that I can recommend. Like there's been this paper by Eldridge et al., the Pomegranate paper, which presents a very early scalable graphics architecture, and it will discuss several of the scalability concerns that we saw were the driving forces behind today's GPU architectures. And the paper is actually quite interesting in various regards, and in particular as it also presents several distributed parallel memory architectures that can be used on GPUs. And this paper is a very interesting read, so I recommend reading this paper. And apart from that, unfortunately, when it comes to GPU architectures, there's pretty much only gray literature that I can refer you to. Like there's the book by Patterson and Hennessy, which also has a chapter on GPU architectures, and much of what is discussed in this book, there's a reference to this book in the slides for part 1 of the lecture. Much of this also holds true, for example, when it comes to caches for GPU architectures, but when it comes to like concrete implementations of those architectures, this is mostly scattered to several documents, some of them from the vendors, like in fact AMD has like a bit of documentation that provides a bunch of insights. NVIDIA has 1 or 2 documents that are also quite interesting, but the information is pretty scattered, and usually like you have like those huge white papers where there is usually very superficial information in that, and then you have to extract the relevant information that is maybe hidden in a few sentences within those documents. So, and apart from those documents by the vendors, there's also a very nice series of blog posts by Fabian Giesen, which is called A Trip Through the Graphics Pipeline. And this blog post actually provides like a lot of hints about how a typical GPU architecture could be implemented. So Fabian Giesen is also a hardware architect, and the blog post is definitely worth reading. It's of course gray literature, like it's not a published and peer-reviewed research paper, but the post by Fabian Giesen provides like a lot of insights into how graphics architectures work, or how they actually could work. So, and with that, we're at the end of the architecture part of this lecture, and we're now going over to discuss how to actually program GPUs. And in terms of programming APIs and programming paradigms, we are now going to discuss general purpose programming for graphics processors, or so-called GPGPUs. And as with every part of the lecture, we'll quickly go over the objectives and what the main takeaways will be. So we already have learned a lot about the characteristics of graphics processors, and we will now apply that knowledge that we gained on how GPUs work and what the general execution model is and how memory works on GPUs. We will apply that, and in particular, we will apply that to other problems than mere graphics. Like, we now understand how a graphics pipeline works on the GPU and how the algorithm is implemented there and which stages are programmable. And we're now moving on to APIs that aren't concerned with graphics in general, but that can be used for general purpose computation. And those APIs make use of the shader cores, of the unified shader cores that formerly were used in order to shade vertices or to shade fragments. And we will now learn how to use them to perform general purpose computations. And we'll thereby discuss the GPGPU programming model. We'll discuss the programming model based on the CUDA API by NVIDIA. But the API is quite general in that the overall programming model when it comes to GPGPU is the same for all the APIs. Like, there's a lot of boilerplate when you, for instance, use APIs such as Vulkan or OpenCL to perform compute, but the execution model in and of itself and the way that memory is exposed and the way that computation and parallelism are exposed are pretty much the same for those various models. And we'll discuss GPGPU programming using the CUDA API, and we will, in the end, be able to program very simple applications that run in parallel and that run in parallel on the GPU. And our discussion will be driven by the CUDA API mostly because it is the simplest API to learn. Like, this, of course, means that we're locked into a certain vendor, but it's not so much about learning a particular API, but it's more about learning a general programming model, that of GPGPU. And what we learn with the CUDA API can easily be applied to other APIs such as OpenCL or Vulkan, or such as other vendor-specific APIs as they are, for instance, developed by AMD. So, and the overall topic here is called stream computing and GPGPU. And GPGPU is basically the answer to many of the scalability concerns that arise from basically the power wall. Like when we discussed Moore's law, and then we learned that Moore's law still holds and that we get this more of transistors every year. And at the same time, we cannot really use them. And the vendors circumvent that by exposing more parallelism on their devices and on their chips. And GPUs are like, they put this to the extreme. So GPUs are basically massively parallel many-core processors. And there's this interesting effect that, on the one hand, GPUs are those tiny supercomputers, and on the other hand, there's this high consumer demand for GPUs, and generally this high consumer demand causes processor prices to be relatively low. So, and the nice thing here is that the high performance computing community usually benefits from that. And this is due to the fact that the chips for the consumer GPUs are usually the same chips that are also used in the professional GPUs. Like the consumer GPUs would be GeForce brand by NVIDIA versus the Quadro or Tesla brand by NVIDIA. And regardless of that they are different GPUs, the chips that are used are usually the same, and there are of course different feature sets in that the professional GPUs usually have better support for instance, double precision floating point operations or for half precision floating point operations that are very important for machine learning. But those feature sets, and if they are activated or deactivated, quite often even comes through the driver. So the chips are basically the same, and the high performance computing segment, which has a demand that is of course much lower than the consumer demand due to gaming, they benefit quite a lot from the fact that the GPU vendors are able to generally manufacture chips quite cheaply because they are manufacturing a lot of them. And everything that I'm saying here, of course, doesn't take the current chip crisis into account, so it will be interesting to see how this will develop over the next months and maybe years. So in this whole process that I just described, that GPUs on the one hand have become quite general purpose in the way that they perform computations, and on the other hand, this synergy that GPUs are relatively cheap to manufacture for the vendors due to this synergy with gaming technology has led to GPUs become quite popular coprocessors for the high-performance computing community. Like, this is a development that started in the mid to late 2000s and is a development that was mostly dominated by the vendor NVIDIA. When we have a look at the so-called top 500, like the top 500 is a list of the most capable supercomputers in the world. And if we have a look at the top 500, and I exemplarily picked the top 500 list from 2017, then you will find that of the 500 most powerful supercomputers, 102 of them use accelerators or coprocessor technology, and 86 of them actually use NVIDIA chips. Like, this has actually shifted a bit in that AMD has become a bit more popular in this community, but nevertheless, this whole process is largely dominated by NVIDIA and is largely dominated by GPU coprocessor technology. As you, for instance, can see on this chart here from 2017, where most of the coprocessors are actually NVIDIA GPUs. So in the very early days, in order to leverage GPUs for general purpose computation, people would basically abuse graphics APIs for that. So they would, for instance, use texture images to upload vector or scalar fields to the GPU, and then they would employ a fragment shader that would perform computations based on those texture images and would write the output to yet another texture which could be interpreted as physical quantities, for instance, on the host. And as you can imagine, this model of abusing the graphics API for general purpose computation doesn't scale very well. So very early on, there were research groups and later also vendors who developed general purpose computation APIs to leverage the GPU power for general purpose computation. And the very early APIs used a paradigm that was called stream computing or stream processing. So stream computing is actually quite similar to SIMD in a sense that instructions are executed on data that is basically streamed through a pipeline. And the instruction sequences are, however, a bit more heavyweight than SIMD instructions. And the instruction sequences are called compute kernels. So in a SIMD processing model, you would basically have a pipeline, and then you would have the stages execute single instructions on the data items that go through the pipeline. And in the stream computing model, you would have like actual instruction sequences, and they could actually be a bunch of sequences, like whole tiny computer programs. And those tiny computer programs are called kernels. So the data is streamed through this pipeline of compute kernels in a structure of array fashion. So this is very similar to SIMD. And the data structures that come to use are FIFOs, so first in, first out queue data structures. And the first APIs that implemented the stream computing paradigm came from the Stanford University, like StreamC, and the Imagine APIs were among the first stream computing frameworks, and they were nowadays replaced by GPGPU frameworks, but they pretty much shaped how GPGPU frameworks work nowadays.
So, and if we were to design a computer algorithm with such a framework, then it might look something like the following. Like we would have like a bunch of compute kernels, and the compute kernels would execute more or less complicated instructions, and the data would be streamed as vectors to those compute kernels. And I'm indicating that by using those queues here. Like the queues indicate that we're using a FIFO data structure. And when you remember back to our discussion of a general GPU architecture, then you might remember during our discussion of the rasterization 2 algorithm that we had a very similar design, where we had the various pipeline stages of the rasterization 2 algorithm, and then we had a deferred model, and we had data such as vertices, triangles, and scan-converted fragments. And those fragments and triangles, etc., they would be temporarily placed in tiny buffers until they could be fed to the various stages of the rasterization pipeline. And you might find that the stream computing paradigm is very similar in that sense, and that the FIFOs that are used to stack up that data that is later passed to the compute kernels behaves quite similar to those small buffers that we also discussed in the context of the rasterization 2 algorithm. So we have that on the one hand, and then we, on the other hand, have a very similar model in that the kernels are very similar to the actual pipeline stages of the rasterization 2 algorithm. So you will find that the overall streaming model is actually quite similar to the execution model that we learned about when we talked about fixed function execution on the GPU. So as a matter of fact, you might actually also recognize the algorithm that I implemented here. The algorithm is just the ZAXP algorithm with the 3 vector inputs and the multiplication and the addition. So, and in the following sessions of this lecture, we will discuss the CUDA API that is used to implement GPGPU programs, and that is highly inspired by the stream computing paradigm. In that, the central element of CUDA is the so-called kernel, which is a tiny program that runs on the GPU shader cores, and that behaves quite similar to a shader actually, in that it runs highly parallel. And on the other hand, it also behaves very similar to the kernels from the streaming paradigm, in that you can model a complex pipeline using multiple kernels. And then we will find that the streaming and FIFO paradigm that we saw in the stream computing APIs can actually be used to leverage the parallel host interface of the GPUs. And all that we will discuss in the following sessions.